Hi community, my name is Dmitry Murzinov. I am co-founder of Deepware. Deepware helps to replace GPU to FPGA. We develop FPGA solution for AI acceleration and helps our client to get a significant advantage over GPU-based solution. I'm going to tell you about neural network inference implementation on FPGA for data centers and edge solution. Before we start, please let me make a disclaimer. This speech don't pretend to deep dive into neural network inference on FPGA. I assume I can designate it just a good entry point in a related topic. Despite this, I hope that by the end of my speech, you will become supporters of the conviction that FPGA offers the optimal trade-off among latency, power, cost, flexibility, scalability, and time to market for data centers and edge applications.
Let me say a few words about my previous background. Most of professional experience has been related to ASIC and FPGA industry. Also, I was engaged in implementation of different subject areas like applied cryptography or digital signal processing in radio frequency band. Don't hesitate to reach out to me on LinkedIn if you have any question for networking. At the first, we will talk about reasons why you should pay attention to FPGA at all. Next, let's take a look at what is the FPGA hardware and what kind of FPGA hardware does the market offers today. The next point, we will consider what optimization are used for implementation neural network inference on FPGA. After that, we will find out what hardware revolution FPGA vendors are preparing for us in the very near future. Next one, using a specific example for recurrent neural network implementation, we will consider whether inference on FPGA can be more efficient than on GPU, and if FPGA can, we will find out how to do. In conclusion, let's summarize what place FPGA occupies in the hardware ecosystem now and what to expect in near future. According to preparation to this speaking, I just typing FPGA DNN in Google and getting interesting search phrase suggestion. Can FPGA beat GPU? I assume that's wrong question. The right question sounds like, why FPGA beat GPU? Indeed, that's really a hot topic and people want to know. Is FPGA the next generation hardware which beats GPU? I should admit the preliminary specification of the RTX 3000 series looks promising, especially significant improvements in neural network engine. Nevertheless, I ask myself, are GPU enough? Good, but not good enough. We will see far. On a line of trade-off on the one hand of which universality and on the other performance, luckily FPGA catch on the center. What we have with GPU, great for high performance computing on batch data. Stable software ecosystem allows easy adoption, but power consumption limit deployment size, not ideal for latency sensitive workloads. NPU, huge performance for specific application, but immature software ecosystem and no clear path to development across generation. ASIC, high energy efficient, but very slow time to market and rigid, can change algorithm after trip out. FPGA absorbs advantages from closest neighbors, namely FPGA have speed, energy efficiency, more memory capability, can be dynamically reprogrammed, provide massive inherent parallelism, blazingly fast in terms of latency, energy efficiency. For better understanding difference between CPU, GPU, and FPGA, let me show the internally kitchen. Scalar processing on CPU, single instruction multiple data processing on GPU, and data flow pipelining on FPGA. Despite both of GPU and FPGA are parallel by design, it's different nature of parallelism. FPGA showing us inherently parallelism by nature, where the entire data flow processing proceeded on pipeline. Unlike CPU or GPU, no predefined instruction set used in FPGA. In this case, we do not need to have a universal computing unit, and they give us an opportunity of deep optimization of each unique pipeline stage. Why FPGA? As you could understand from the previous slides, FPGA are huge sea of generic logic and interconnect. FPGA looks like silicon layers, build them into exactly the right circuits for each task. Let's move on to 6 facts. Ultimate performance. Special proposed hardware like FPGA is faster than and more efficient than general proposed hardware like CPU and GPU. Massive inherent parallelism by design. FPGA exploits different forms of parallelism than auto acceleration. Flexible and scalability, its ability to run multiple neural networks on one instance. Also, custom memory hierarchy, flexible data types with any digit resolution down to work with binary digit even. Can be dynamically reprogrammed hardware anytime, about 100 milliseconds is reconfiguration time. About secure, I'm not proficient as information security expert for confidence consideration about threat model, but let me put in my 50 cents. My goal is to provide information about the powerful security features that has FPGA to work with sensitive data. It contains FPGA gateware image encryption, FPGA gateware image signing, and secure board updates. Helps to prevent loading or executing on unauthorized workloads. Provides anti-rollback capability that helps to prevent execution of old or outdated design. And help to prevent unauthorized access to key interfaces and onboard flash. Okay, we got two most important things: low latency and energy efficient. FPGA designed for full utilization of silicon resources, unlike CPU or GPU. No predefined instruction set used in FPGA. FPGA operates with a small batch of 4 efficient responses. FPGA have a bunch of on-chip static memory for reduced external memory traffic. Indeed, these are the things that make it possible to competition with the GPU. Further, this topic will be covered in more detail. Why are FPGA so energy efficient? As we all know, large data movements proceed in AI algorithms. Data movements become the main bottleneck for improving the energy efficiency, because energy efficiency of dynamic memory is approaching its limit. Thanks for FPGA that have multi-level memory for flexible trade-off tuning. Large memory of static internal memory allow us to reduce external data movements. Another significant approach to decrease power: no predefined instruction set used in FPGA. Thanks to silicon layers for opportunity to optimization for unroll and customized pipeline stage. This is FPGA programmable accelerator cards for use in data center and clouds. Here are solutions from 3 different FPGA vendors. Despite the fact that here provided solution can be bought and used today, all of them are made with the latest cutting-edge technology and tape out from 7 to 16 nanometers. Especially, I would like to focus on the size and bandwidth of the on-chip memory. Why on-chip memory bandwidth is so important, we will return a little later. Also, pay attention to the advanced communication capabilities of the high-speed network interfaces. The standard gentleman's bundle includes a couple of 100 gigabit per second QSFP interfaces. Also, find their place in specific application, as an example in low latency and even ultra-low latency application. Like a real-time solution for autonomous driving, LiDAR, advanced driver assistance system, computer vision, industrial and manufacturing automation. In recent years, there has been a trend to use AI in the factories. In such system, data from sensor is directly connected and processed inside the FPGA. In this case, we are even more tightly squeezed into the limitation of the system response and energy efficiency. The edge device poses challenges in power and bandwidth. For fine-tuning power latency bandwidth ratio, vendors provide broad device range. Scalable device family for different applications can provide low power or ultimate memory bandwidth solution. The last is key to ML inference performance. Here is a list of implemented enhancements by various FPGA vendors for the AI era. As we can see, there are 3 primary groups. DSP, which means multiplication and addition improvements, mainly related to accuracy reduction or supports of block floating point unit. Memory in terms of increased size, flexibility and bandwidth of external memory interfaces. The last one, domain-specific architecture with a specific engine and network-on-chip capabilities that shifts the FPGA on trade-off line closer to the NPU. If you want to learn more about how to FPGA vendor prepare to coming AI era, I highly recommend specified paper to read. There is examples of next-gen FPGA. XILINX Versal family, Intel Stratix 10NX family, and Acharonics Speedster 7T family. Let's take a closer look at what changes have occurred using an example of the Intel Stratix 10NX FPGA fabric, which includes new types of AI-optimized tensor arithmetic block called the AI tensor blocks. These blocks contain a dense array of low-precision multipliers typically used in AI application. The AI tensor blocks architecture is tuned for common matrix-matrix or vector-matrix multiplication, used in a wide range of AI computation with capabilities designed to work efficiently for both small and large matrix sizes. The AI tensor block multipliers have a base precision of integer 8 and integer 4 and support floating point 16 and floating point 12 in numerical format through shared exponent supports hardware. All additions and accumulations can be performed with integer 32 or IEEE 750 for single precision floating point, and multiply AI tensor block can be cascaded together to support larger matrices. A single AI tensor block is estimated to achieve up to 15 times more integer 8 throughput than compared to standard Intel Stratix 10 FPGA and DSP block. If everything is so good with FPGA, you can ask me why have not FPGA become such widespread as GPU. Firstly, FPGA vendors just recently have turned their attention to server and data center market. What do I mean? This was made possibly by success of the semiconductor industry. I mean today the modern FPGA are comparable to GPU in terms of chip area. These FPGA are too expensive but stay available for enterprise market. The second reason is the development speed and the need to have engineer with combination of software and hardware skill in the team. Programming has been a barrier in the past which needs several months to deploy. Today, with the help of OpenCL, you can get simple code portability from existing CPU and GPU code. The third reason is that the compile loop is usually too long, from fixing something in source code to getting an image that can be loaded into FPGA. We'll pass several hours to synthesize and place and route procedures. The next reason is related to the previous one, FPGA size and complexity. Huge design space and die area related to hard to optimize application. FPGA size directly affected speed and numbers of accelerated tasks. And when, where, what, how to accelerate. The next one, hard to evaluate, I mean cost. FPGA is still too expensive for I just wanted to try it. Please note that several companies already provide acceleration as a service in cloud, for example Amazon. I guess most of these terms are familiar for open data science community, so let's move on to hardware generation part now. This is a section about software tools that use knowledge of the FPGA internals and take different approaches to implement design. The traditional approach uses RTL languages like Verilog or VHDL. This way needed several months to deploy. Sorry, nothing personal, but this approach is still used in case to requiring best-in-class result. This is due to the fact that you can implement all sorts of low-level tricks or know-how. For example, DSP multi-pumping techniques where DSP blocks clocking at doubled frequency. The new wave has given us some new tools. For example, Intel 1AP, a unified data parallel language which allows code reuse across hardware targets and enabled high productivity and performance across CPU, GPU, and FPGA architecture, while permitting accelerator-specific tuning. Next one, XILINX YTS HLS, a unified platform, enables the development of accelerated application on heterogeneous XILINX platforms with single design methodology and programming model. The last one is OpenCL. Third-party tools provide simple code portability from existing CPU and GPU code. Next innovative step in industry is move from traditional design flow to so-called pure software approach where no FPGA expertise is required. On the left, all aspects of the design are captured in a single bitstream. A data scientist may be able to design at high-speed level, but the tools pass through the aspects of the design through the hardware compiler. On the right side, the high-level model data is captured in the separate binary file. The exact point at which changes to model might require hardware bitstream change will vary by FPGA vendor. We will program FPGA with no code change soon. Let's get back to the topic of model optimization and look at the FPGA optimization detail. Reduce the number of bits used to represent number models are usually trained at 34 bits. This is not necessarily needed in real life. Usually we could reduce numbers resolution to 8 bits without losing precision. Usually it's allowable negligible accuracy loss with 8-bit fixed point write and activation. At the same time, as we can see, the FPGA resources utilization decreased significantly. The programmable logic inside an FPGA offer the unique capability to customize the resources of an arithmetic operator with very fine granularity to exact number of bits that are required to the application. Thereby, the application can exploit the potential to reduce the hardware cost for the compute along with the memory. The quantization scheme can be uniform or non-uniform, and different quantization schemes can be used for different parts of the network. Using fewer bits required much less computer and memory, but might result in less accuracy. Many recent publications have proposed better quantized training techniques. Parts of neural networks can be run away without any significant impact on accuracy. As much as 90% for some layers. Pruning techniques differs in how the pruned parts are chosen. For example, by wide magnitude or second-order derivatives and in the granularity at which pruning is performed. For example, individual synapses, adjacent group of synapses, or entire feature maps for convolutions. Pruning individual synapses results in irregular structures that can only be processed efficiently by specialized hardware. While coarser granularity pruning is typically preferred, finely granular pruning offers further performance scalability that can be exploited with FPGA, tailoring a memory subsystem to efficiency store sparse representation while supporting the implementation of computing engines. Here is an example of distributed hardware using multiple FPGA to perform a complex task. Thanks to high-speed external interfaces, usually up to 200 gigabit per second, we can slice the large network into several parts by mapping them in different FPGA cards. It allows us to use as many nodes as necessary. By example, if a card has at least 2 QSFP ports, we might be using the ring topology. Do we have reserve to further reduce latency? I think so. The most obvious way to move preprocessing inside FPGA, for example, in case of speech-to-text, it will be Fourier transform. The next one is data plane development kit, development by Intel and managed by the Linux Foundation. DPTK is a set of libraries and drivers for fast packet processing. It moves processing from kernel to user space. Despite DPTK has no direct impact on latency, it is important technology for overall CPU offloading, which is widely used in HPC for network cards. The next approach to receive tasks directly via the high-speed network interfaces. Because data movements in most accelerators have a high latency link, such as PCI Express. Also, huge memory transfer between host and accelerator might degrade fast response too. The last one is experimental and implied direct storage connection to FPGA through PCI Express lanes, similar to RTX I/O, but not exactly. There is illustration of FPGA capabilities for CPU-less setup. It's still not yet a production setup, but this promising setup which will further dramatically increase energy efficiency by eliminating the CPU and complying subsystems. In this setup, assume that we receive tasks via the high-speed network interface, and on the storage we have a collection of gateware, FPGA images, and a set of weight of various neural networks. Okay, return to architectural features. Memory multiply accumulate array distributed across the entire chip, and the model located in memory tightly to the math engine. The computer mechanics and data input-output logic designed in according to reduce overall latency. A similar architecture was implemented in silicon for the next generation FPGA for AI. Visualization of this architecture principle in the picture on the right. What does give us corresponding architecture? For tasks using recurrent networks on the GPU, when working in real time with minimal latency, i.e. with a batch size 1, there is a significant drop in GPU performance compared to the calculated one. A similar case on GPU when working with small batches on convolution network, but in case of recurrent networks, we getting dramatically penalty on performance. The root of evil is the use of fully connected layers. In recurrent networks, it's the operation of multiplying vector by a matrix. In this operation, each byte of the matrix is used for inference just only once. And due to the need to load new coefficient from memory at each GPU clocks, performance and hardware utilization rate to hard decrease. In contrast to this, FPGA has custom memory hierarchy. It means near memory compute and programmable routing for data reuse. For Tesla V100, memory bandwidth shown in technical specs. For FPGA, here are the bandwidths for custom neural network, which we will look at in detail on the next slide. Here, FP24 is custom format of floating point. 24 bits used for number representation, and we can place 3 numbers value into ultra RAM data width. 3300 its amount of multiply accumulated blocks in case of this network, and 550 MHz is achievable FPGA working frequency in this case. Here evaluated theoretical achievable performance for 2 kinds of hardware card. This estimation based on memory bandwidth limitation in both cases for GPU and FPGA. Besides, for FPGA, in this estimation used only internal static memory, in accordance with our previous knowledge of the difference in power consumption of dynamic and static RAM, external and internal memory respectively, we can suppose conclusion about the difference in energy efficiency. Now, a few words about common delusion related to FPGA in neural network deploy. Low awareness of pragmatic substitutes for GPU and fair benchmarks, like apple-to-apple comparison. I mean, for example, manipulation of benchmarks, providing peak performance or measuring by fortunate conditions, example gratia large batch size. Usually, DNN architecture should over-design to mitigation fundamental GPU's limitation. Due to this, instead of investing in product enhancement, engineers should involve in performance race. Single FPGA equals to single task. Remaining time, FPGA will in idle mode. It's not true. FPGA might be used in wide range of payload with reconfiguration time about 100 milliseconds on the fly. But available of well-qualified guy to starting play around FPGA DNN. It was true for obsolete design tool, which needs a lot of hardware needs. Today, with modern approach, I mean high-level synthesis and evolution of powerful design tools, this issue can be significantly reduced or completely eliminated. Lack of quality FPGA DNN turnkey solution providers. I know at least several companies which have deep expertise of DNN on FPGA. There is a number of FPGA neural network solution vendors. As Deepware, we provide neural networks with comparable performance from other competitors. Next step is to support transformer and RNN transducer introduced by Google. To be honest, at this moment, is it difficult to estimate benefit size can be obtained on FPGA. In conclusion, where FPGA are good enough? Key advantages for DNN on FPGA include higher performance per price. Here I mean inference per dollar. Lower inference latency with batch size 1, without inference per second degradation. Lower power consumption normalized to performance. Let's summarize what place FPGA occupied in the hardware ecosystem now and what to exists today or expect in the near future. First one, demand of reduction total cost of ownership, usually actual for large data centers or facilities of cloud providers. They might provide FPGA as a service. Next one, low latency application. It various cases usually associated with enhancement of user experience like speech-to-text, speech synthesis, machine translation. And last one, ultra low latency application, for example, real-time solution for advanced drive assistance system, autonomous driving, LiDARs, drones, high-frequency trading, almost all implementation of it's based off embedded hardware. Finally, we have reached the end of the presentation. I hope you found my speech useful. Now we can proceed to the section of question and answer. Welcome to special chat. Also don't hesitate to reach out me on displayed areas in messengers. Bye.